question because nobody is watching them. So we said that there were two conditions. We can generalize this from convex functions. If the sum of the GIs are affine functions, and if they are not affine, they are locally convex. So they are in the neighborhood of the point x tilde, they are convex. Then we have this condition that the cone of feasible direction satisfies is exactly the same cone as here, so the intersection of half spaces. And now we have earlier, we had already proven the, so that we know that if the function has a relative minimum at the point x, it is, so if I take any point from our constraint set or from this cone of feasible direction, the gradient of the function f of our cost function, and you take the scalar product with the z minus x, this is a direction. It's a feasible direction. Then the scalar product is non-negative. So you are not able to decrease the costs anymore if you are going away from this point x, any direction, any feasible direction. Which in the same time means that F0 and D, so this the cone of feasible directions and the cone of improving direction, they have empty intersection. They don't have common points or common vectors at all. So I had here in my last week, I had the following constraint optimization problem. So I minimize a function which is quadratic in x1 and x2. So clearly the function has a global minimum at the point with coordinates 2 and -5. But
Sorry,
this,
excuse me, we cannot see the slide you're showing on the board.
okay, what happens here? So the global minimum of our quadratic function is not contained in our constraint set. So the global minimum, if we look at here, so it's somewhere here, the coordinates are 2 and -5. It's here. So here is the global minimum. So it minimizes our cost function in R2. But this 2 minus 5 is not contained in the constraint set. So we have to look for a minimum in the constraint set. We have here this 2 parabolas, and the constraint set is here. And I have drawn with the red lines the boundaries of the cone of feasible direction. And then I have drawn at the point with coordinates 2 and 2, I have drawn the black line, which defines the cone of improving directions. It's a half space. So if I go from the point 2, 2, if I go into that direction, so that the x2 value is less than 2, then it's the improving direction. But immediately when I leave the set, the constraint set, so it's less than 2, then I'm out of the constraint set. So in this point, on this boundary point, my cone of feasible direction is here, and my cone of improving direction is the half space before this black line, below the black line. So there is no common points. So there is no vector, non-zero vector D in such a way that it belongs to both sets. So it means that we have exactly our theorem that X is a minimum point in our constraint set is equivalent that these two cones have an empty intersection. So for example, let's take the following example, the next one. So I draw a circle. Like this. And then I have the line x1 plus x2 minus 1 is less than 0. It is, for example, like this. So this is x1 plus x2 minus 1 is less than 0. Let's have first the coordinate system somewhere. So here we have x1 coordinate and x2 coordinate. And the constraint set is here. Then you take the circle or these disks. It is the so it's centered here. So if the equicontour lines they are x1 minus 1 squared plus x2 minus 1 squared is equal to some constant capital K, which is of course non-negative number. And of course, if this number is big enough, the optimal value, we choose the smallest K in such a way that this circle touches the constraint set. So the circle must be tangent to the line x1 plus x2 minus 1. So we take a circle like this, and we increase it a little bit like this. And there we have the smallest circle that still touches the constraint set. like this. And of course, using elementary geometry, we can compute exactly what is the radius. So when this boundary of the constraint set, the line x1 plus x2 minus 1 equals to 0, is tangent to this circle. So we can compute it. Then let us draw a picture. So at the minimum point, I put it now here, the coordinates, for example, Z1 and Z2. The gradient of our cost function, what is the direction? And it points sorry. Oh. What do you mean? No. Anyway, it's close enough. And then we compute what is the normal vector of our constraint set in the point Z1, Z2. So it points I have to like this. So these two vectors, the gradient of the point, sorry, here should be Z1 and Z2. So these two vectors are, they must be in the same direction, so they are linearly dependent. So I can find a number in such a way that if I multiply this gradient vector with some constant, I have to get the gradient of f. So this is the only explanation. So it is the minimum point. At the minimum point, these two vectors are linearly dependent. And this is what I'm trying to tell. So in every case, so if I have several of those constraints and I have a candidate for a minimum point, then the minimum point must satisfy this condition that you take the gradient of the cost function at the point. It must be a linear combination of these gradients of those constraint functions at the same point. So let's return back to our original problem. I had these two here, these two constraints. So two parabola, intersecting parabolas, the constraint set here. And I justified that, okay, the cone of improving directions is below, it's a half space below the line, the black line. And the cone of feasible direction is here, this red wedge. And optimality criteria is that these two cones have empty intersection. So I claim that this 0.22 is a minimum point. It has the same property as in the previous example, that at this point the equicontour line is a tangent. It touches only at one point the constraint set. If you take the ellipse a little bit smaller, then these points are not anymore in the constraint set. And if you take the ellipse a little bit larger, then there is points where the cost function gets smaller values. So this is the optimum point. And if I compute the gradient of the cost function here, it points upwards. So it points to the x2 direction. If I take the gradients of the constraint functions, they are pointing into this direction. So there is, it's cannot be seen here, it's W and V. W is the, here the is the constraint or the gradient of the function G2 here. And V is the gradient of the function G1 at the point 2, 2. Here I have computed. So the gradient of the cost function at the point 2, 2 has coordinates 0 and 2. And the gradients of the constraint functions are 2 and -2 and -16 and -16. And I can find positive constants in such a way that this linear combination goes to 0. And this is what is called the Karus-Kuhn-Tucker conditions. It has positive Lagrangian multipliers, 1/2 and 1/16. So exactly the same way as in our simple example here, this one actually, now if I take the point Z1 and Z2 they are both negative, actually this vector points into that direction. Because Z1 is obviously a smaller number than -1, so Z1 is less than 1, so this is negative. Z2 is also negative. So here also we must have the condition and obviously this mu is something, it's positive. So if I take the conditions here, so from the first condition I get Z1 equals 1 minus mu over 2. Z2 equals also 1 over minus mu over 2. Z1 and Z2, it's the point on the boundary of our constraint set. Z1 plus Z2 minus 1 must be 0. So we have 2 minus mu minus 1 is 0. So, sorry. Yes. U equals to 1. And then we can solve the minimum point. Is is 1/2 and 1/2. So this one I have to now prove that it is always like this. So I will use in the proof this Farkas lemma. So if this is a very important statement. So if I have any matrix, a real matrix, M times N matrix, there is only 2 options. So there are 2 alternatives which hold. We have a vector D in Rn such that A times D has negative coordinates. And if this is not possible, then there is a non-negative vector P such that A transpose times P equals to 0. The proof is quite long, and I won't do it because we have to go more into details of convex analysis, and we don't have time for that. So I take it as a given. So let X tilde be a feasible solution. The index set IX tilde is the set of active constraints. And of course, for simplicity, we assume that F and GIs are convex differentiable functions in such a way that if I take the vectors, the gradients of the constraint functions at the point X tilde, and only those which are active, and I assume that they are linearly independent. Why I take only these active constraints? Because if GI is inactive, so to speak, we can forget it. We don't have to take it into account at all. It doesn't constrain our costs at all. What does it mean that if they are linearly dependent? It means that it's the same as you have 3 lines intersecting at the same point in R2. And once again, you can drop one of these lines away because the point is in plane is defined by intersection of exactly 2 lines. So we can drop one of these lines. So we can always make this assumption that we can take a linearly independent set of vectors from these vectors which are active at the point X tilde. And then we assume that X tilde is a minimum point. Then I claim that there are non-negative numbers ui such that the gradient of f at x tilde plus this linear combination of the gradients of gi's equals to 0. Exactly as in our example. So, and this one, the proof of this is what we call Karus-Kuhn-Tucker condition. I will write it in a different form later on. But, and actually what we have here is more or less just a generalization of the classical Lagrangian multipliers. At least our students here in Oulu, they study in Calculus 2. They study the method of Lagrangian multipliers, but they have equality constraints. Now we have inequality constraints. About the proof. If x tilde is a minimum point, there is no vector d such that it is contained in F0 intersection of the cone of improving direction and in the cone of feasible directions. So it means that this set is empty. So I define the matrix A, where I take as a first row. This is first row is the gradient of f, and then the next rows are the gradients of the constraint functions, active constraint functions. So it means that this relation is inconsistent. So we have two options. Either there is a vector d such that AD contains strictly less coordinates, or we have a non-negative vector b such that the A transpose times P equals to 0, and P is non-zero vector. And I denote this vector B, its coordinates are B0, and then comes coordinates which are related to the active constraints. What is the matrix A transpose? The first column of this A transpose is the gradient of F, and the rest of the columns are the gradients of the constraint functions. So A transpose times P is this linear combination, and it must be 0. And we know that this vector B is non-zero. Is it possible that P0 is 0? No, it's not possible, because if P0 is 0, this part, so the gradient, this one vanishes. And we have left that the linear combination of the gradient vectors of this constraint, gradients of the constraint vectors, the linear combination is 0. But because the gradients were linearly independent, it is possible only when Pi's are 0. But then it means if P0 is 0, so it implies that all the rest coordinates are as well 0. But it was impossible because by the Farkas lemma, B must be non-zero. So B0 must be non-zero. And then we choose UI equals PI divided by B0. These Lagrangian multipliers are non-negative. So we have this condition for our minimum point. So it is a necessary condition. So if I have a minimum point, then there must be these Lagrangian multipliers in such a way that this sum of gradients must be 0 with non-negative coordinates UI. Okay, what about if I have inactive constraints? I put this Lagrangian multiplier 0. I can multiply any vector with the 0. It doesn't change this relation. So if I doesn't belong to active constraints, I set UI equals to 0. So the form we use, where we use these Karus-Kuhn-Tucker conditions, is as follows. X tilde is a minimum point. Then there must be non-negative numbers UI such that this relation, this linear combination goes to 0. And then if UI is positive, then we must have GI X tilde is 0. So we have a active constraints. And if the constraint is inactive, UI must be 0. This is just a vector short form writing the same thing here. And this is the way how to find the minimum point. So it is, now we have some kind of a algebraic system how we compute the candidates for the minimum point. Remember that this is a necessary condition. So if a point satisfies these conditions, it is not guaranteed that it is a minimum point. So we must require something more so that it is a sufficient condition as well. And then, of course, we can generalize this one to problems which are non-convex. Only that we consider a small neighborhood of the, so then we could speak only about local minimum. So then the converse. Let X tilde be a point which satisfies the Karus-Kuhn-Tucker conditions. And we assume that all constraints are active. Then if F and GI are convex differentiable in the neighborhood of this point X tilde, then X tilde is a local minimum. And of course, if F and GI are globally convex, then x tilde is the global minimum. If f and gi are differentiable and f is pseudo-convex, so means that if we have this condition valid, remember that this condition was necessary and sufficient condition for Z to be minimum point in convex optimization. But if this condition implies that Z is a minimum point, we speak about pseudo-convexity. So it is a little bit more general than convex. So we can, and the level sets of the constraint functions are convex, then X is global optimal solution. So in this case, the Karuskun-Tucker conditions are also sufficient conditions. So for example, I will prove the sufficiency only in the case when f and gi's are convex. So let's assume that x is any point. And we have fx tilde is of course less than fx tilde minus lambda I times gix for any lambda I which is non-negative, and gi's at x are non-positive. So this number is negative and we multiply it by -1. So this right-hand side here is for sure larger than the left-hand side. And remember that if I belongs to the is active constraints, this one is 0, so we add nothing. And lambda I equals to 0 when I is not here. So here should be also x tilde. So with this condition, lambda I times gi x tilde equals to 0. So here we have exactly equality valid. Then we know that gi is a convex function. So this one is greater than the gradient of gi x tilde scalar product with x minus x tilde. It was the equivalent definition for convexity. Okay. And then I multiply it with -1. So then I have the inequality reversed. But this one here the minus, this is independent of the summation. X minus x tilde is independent. This is here, or minus the sum here, is actually the same as gradient of f at x tilde, because I assume that the x tilde is a point which satisfies the Karuskun-Tucker conditions. So we have this condition. So fx tilde is less than fx tilde plus gradient of f at x tilde scalar product with x minus x tilde. But f was a convex function. And by the definition of convexity, it's less than fx. So we have proved the case that for any point x, the cost at the point x is bigger than the cost at the point x tilde when x tilde satisfies the Karus-Kuhn-Tucker condition. So x tilde is a minimum point. The same proof can be extended to these non-convex cases where we take only local environments of the minimum points. So we consider everything locally. We have a locally convex case. Then the same proof, a little bit more lines, but exactly the same proof is valid at that case also. Okay, let's take here one example. So let us take cost function which is linear, and the constraint set is the disk, which boundary is a circle, the center is at the origin, and the radius is square root of 3. So let us use the Karus-Kuhn-Tucker conditions. So our function f, here is the linear function, x1 plus 2 times x2. We can compute the gradient at every point x1 and x2. It is always the same. It's the gradient is constant. It's with coordinates 1 and 2. So into that direction, if I'm locating in any point in the plane, in that direction, the function grows the most. Then I have just one constraint function. It's quadratic, x1 squared plus x2 squared minus 3. And then I compute the gradient of g. So it is 2 times x1, 2 times x2. The gradient condition in the Karuskuntaker condition says that at the minimum point, gradient of f x plus mu times gradient of g at x equals to 0. So gradient of f is with coordinates 1 and 2 plus mu times 2 times x1, 2 times x2 equals a 0 vector. And there we get a condition which says that 2 times mu times x1 plus 1 equals to 0. 2 times mu times x2 plus 2 equals to 0. And we know that mu must be, the Lagrangian multiplier must be non-negative number. So we have used here the gradient condition. Is it possible that this Lagrangian multipliers equals to 0? Why it is non-zero? Because if the Lagrangian multiplier is 0, then we end up a contradiction. 1 equals to 0. It is a contradiction. It is impossible. We must have mu positive. Then we use the complementary slackness. So we have mu is now positive. And then in the Karuskuun-Tucker conditions, we had that the product of mu and the constraint at the minimum point equals to 0. So mu times Gx equals to 0. And then, of course, we have to remember that Gx must be also less than 0. But because mu is positive, Gx must be 0. So we must have x1 squared plus x2 squared minus 3 equals to 0. We can solve here x1. It is minus 1 over 2 mu. And x2 is minus 1 over mu. So we get the equation for here. We get from here the equation 1 over 4 times mu squared plus 1 mu squared minus 3 equals to 0. So actually, let's write it here. So it is 5 divided by 4 times mu squared minus 3 equals to 0. And you get equation 12 times mu squared equals to 5. And mu is plus square root of 5 divided by 12. There is 2 solutions for this equation, but the other one is negative. We have to choose the positive one. And now we have solved the case. So we get the minimum point is -1/2 times mu. So it is minus, you multiply mu with 2, so you get here 3 over square root of 3 over 15, and minus 1 over mu. So it is minus 2 times square root of 3 divided by square root of 5. This is our minimum point. So this is in principle the way how you use the Karuskun-Tucker conditions for finding the minimum point. So some kind of an interpretation. So if we write, so assume that we know this x tilde somehow, or we know these Lagrangian multipliers at the optimal point, at the minimum point. Then the gradient condition is nothing else than minimizing this function at the whole space. Because if I take the gradient of this function, it is 0 at the point x tilde. So it's the minimum point of this function, capital F. But of course, I don't know in the very beginning what are these true Lagrangian multipliers. So actually the first condition, the gradient condition, is just the optimality criteria for an unconstrained problem. Let's take some problems where we have which are very usual in optimization. So in very often we have a quadratic optimization problem. So we have here a matrix A. I assume that A is symmetric and positive definite. B is just some known vector. Then this objective function is convex for sure. Our constraint, we have a constraint matrix from, it's a m rows and n columns. So it's the linear set of constraints. So it is a convex set because it is an intersection of half spaces. So in this case, we don't have to worry about that. If we find the point which satisfies the Karuskun-Tucker condition, it is immediately the minimum point. Maybe there is several points which satisfy the Karuskun-Tucker conditions. It is quite possible. So if we want to find the minimum point, so we first compute the gradient of the cost function. It is a times x minus b. If we take the gradients of the constraints, so if I compute the gradient of the first constraint, it is just, I wrote this matrix C in such a way that there is it's the first row, second row, so there is m rows. And if I compute the gradient of the first row, it is just the column vector, which is the first row of the matrix C. So the gradient condition for to be a minimum point is the gradient of f plus the linear combination of the gradients of the constraint functions, or the linear combination of the row vectors of the matrix C with some Lagrangian multipliers which must be non-negative. We have computed here ax, the gradient of f, it is ax minus b. And then we add there the linear combination of the row vectors of the matrix C. So we have here, this one is nothing else but the C transpose times U bar. I have denoted by U bar the vector which has the coordinates ui. So it is the vector in Rm. And it has non-negative coordinates. The matrix A here was assumed positive definite. So this linear system of equation has for sure a unique solution which depends on the Lagrangian multipliers. So you can solve this one for x. And then you have the complementary slackness condition. So you take the scalar product of u with cx minus d, it must be 0. Lagrangian multipliers are non-negative, and cx minus d is the vector with all coordinates non-positive. And then we can solve this one. So let's have a look if we have time enough. So I take and now so here I have my example. So we have a quadratic optimization problem. The matrix A here is clearly positive definite. It's 2 by 2 matrix. Diagonal elements are 4. And off-diagonal elements are -1. Vector B has coordinates 3 and 3. The matrix C, I have just one constraint now. The matrix C is with coordinates 1 and 1. And D is 1. Okay, I have provided already what is the solution. So the Lagrangian multipliers must be 3/2, and the optimal or the minimum point is with coordinates 1/2. Okay, let's see if I can get it. So we write Karuskun-Tucker conditions. First, we have the gradient condition. So gradient of f at x plus, we have just one constraint, mu times gradient of g, x equals to 0. So remember that gx now is here. C transpose times x, minus 1 is less than 0. So gradient of f is a times x minus b plus u times, and the gradient of the vector g is the vector c is 1, 1. So I have here 4 minus 1 minus 1, 4 times x1, x2 minus the vector b, so 3, 3 plus u times the vector with coordinates 1, 1. And this must be 0. So we have a linear system of equations. So what we can do, we now, for example, we can multiply the second row by 4 and add it to the first flow. So if I multiply the first row with 4 and add to the second one, I get here 0. Then I have 16 minus 1, so I have here 15. Second row remain untouched. And on the right hand side, I have 12 plus 3, it's 15. and -5 times u. And the second component is untouched, 3 minus u. And here we can solve first. X1 is 1 minus u divided by 3. And the second coordinate, we have 4 times x2 equals 3 minus u plus x1. So it is 3 minus u plus 1 minus u over 3. So it is 4 minus 4 over 3 times u. Sorry? Yes, x1. So sorry, yes, x2. Actually, it doesn't matter because it is it's symmetric, so it should be. So here is x2 and so here I have minus x1 equals 3 times 3 minus u minus 4 times x2, 3 minus u minus 4 times 1 minus u over 3. So it is -1 and 4 over 3 minus 1, it is plus u over 3. And we get here that x1 equals 1, x2 1 over u minus 1 minus u over 3, and x2 is also 1 minus u over 3. Is it correct? Yes. Okay, let us continue from this on Wednesday morning.